The Big Bang Theory suggests that the universe began with a singularity, a point of infinite density and temperature. However, this concept poses a paradox when considering our current understanding of physics, particularly general relativity and quantum mechanics. According to general relativity, the laws that describe gravity and the behavior of large-scale objects, singularities, are problematic. They are points where the curvature of spacetime becomes infinite and our equations break down. Singularities are typically associated with black holes, where the matter is compressed to an extreme degree. However, the singularity at the beginning of the universe would have been even more extreme, surpassing any known physical limits. Quantum mechanics, on the other hand, governs the behavior of matter and energy at the microscopic level. It provides a framework for understanding the behavior of particles and their interactions. However, at the singularity, quantum mechanics and general relativity collide, and our current understanding cannot fully explain what happens under such extreme conditions. The singularity paradox raises doubts about the plausibility of the Big Bang as the true origin of the universe. It suggests that our current understanding of physics is incomplete or that alternative explanations may be required to account for the universe's origin. Scientists are actively exploring theories such as loop quantum gravity and string theory, which attempt to reconcile general relativity and quantum mechanics and provide alternative explanations for the origin of the universe. While the singularity paradox challenges the Big Bang Theory, it is important to note that scientific knowledge is continually evolving. Supporters of the Big Bang Theory often point to the discovery of cosmic microwave background radiation as a key piece of evidence. The CMB is a faint, uniform radiation that permeates the entire observable universe. It is often considered a remnant of the early stages of the universe, approximately 380,000 years after the supposed Big Bang. However, some alternative explanations challenge the interpretation of CMB radiation as definitive proof of the Big Bang. These alternative explanations propose that the CMB radiation could be the result of other astrophysical phenomena or artifacts, rather than direct evidence of the Big Bang's existence. One such alternative explanation is known as the plasma cosmology model. This model suggests that the CMB radiation arises from the interaction of electrically charged particles within the universe, rather than from the aftermath of a Big Bang event. According to this model, the CMB radiation is produced by electromagnetic processes occurring in large-scale structures such as cosmic filaments and galaxy clusters. Additionally, critics of the Big Bang Theory argue that the interpretation of CMB radiation as evidence for the Big Bang relies on certain assumptions. These assumptions include the assumption of isotropy, uniformity, and the assumption that the observed radiation originated from a single, highly energetic event. Skeptics argue that these assumptions may not be entirely justified and that alternative explanations for the observed CMB radiation should be explored. The horizon problem is a challenge to the Big Bang Theory that arises from the observation that different regions of the universe have similar temperatures, despite being located far apart and beyond each other's range of causal contact. According to the theory, these regions should not have had sufficient time to reach thermal equilibrium and establish a similar temperature. In the early universe, before the period of recombination when atoms formed, the universe consisted of a hot, dense plasma of particles and radiation. As the universe expanded, this plasma gradually cooled down. However, due to the limited speed at which information can travel through the universe, regions that were initially in contact became causally disconnected as the universe expanded. According to the Big Bang Theory, the horizon problem is addressed by the concept of inflation. Inflation suggests that during an extremely brief period in the early universe, the universe experienced a rapid and exponential expansion. This expansion would have stretched out the universe, making regions that were previously in contact much larger and allowed them to reach thermal equilibrium. However, the mechanism and fine-tuning required to achieve this uniformity through inflation remain unclear. Inflation would have needed to occur with incredible precision to ensure that different regions of the universe had similar temperatures and properties. The specific conditions and dynamics that would lead to such uniformity are still the subject of ongoing research and debate. Critics of the Big Bang Theory point to the horizon problem as a potential flaw, questioning whether inflation or any other mechanism can truly account for the observed uniformity of the universe's temperature. Alternative cosmological models, such as the cyclic model or the plasma cosmology model, propose different mechanisms to explain the observed homogeneity without relying on inflation. The flatness problem is a challenge to the Big Bang theory related to the geometry of the universe. The theory assumes that the universe has a flat geometry, meaning that the sum of the angles in a triangle is exactly 180 degrees and parallel lines never intersect. However, observations suggest that the universe is incredibly close to being flat. According to the theory, the geometry of the universe is determined by the density of matter and energy within it. If the density exceeds a critical value, the universe would have a closed geometry, positively curved, like the surface of a sphere, and if the density is lower than the critical value, the universe would have an open geometry, negatively curved, like a saddle. Only if the density precisely equals the critical value would the universe have a flat geometry. The flatness problem arises from the observed near-flatness of the universe. It is remarkable that the density of matter and energy is so finely tuned to be extremely close to the critical value. Even a slight deviation from this value would lead to a significantly curved or non-flat universe. The probability of the universe having such precise flatness by chance alone is remarkably low. It suggests that the initial conditions of the universe must have been finely tuned to an extraordinary degree. This fine-tuning is difficult to explain within the framework of the Big Bang theory without invoking additional mechanisms or concepts. To address the flatness problem, alternative explanations have been proposed. One such explanation is the concept of cosmic inflation, which we mentioned earlier. Inflationary theory suggests that the universe underwent a rapid expansion during its early stages. This expansion would have smoothed out any deviations from flatness, making the universe appear nearly flat today. One of the challenges posed to the Big Bang theory is the observed asymmetry between matter and antimatter in the universe. According to the theory, during the early stages of the universe, equal amounts of matter and antimatter were created. However, our observations indicate an overwhelming abundance of matter, with very little antimatter. Matter and antimatter are composed of particles with opposite charges and other properties. When matter and antimatter come into contact, they annihilate each other, converting their mass into energy. This process is well understood and has been observed in laboratory experiments. If equal amounts of matter and antimatter were created in the early universe, one would expect them to annihilate, leaving behind only radiation. However, our observations indicate that matter dominates the universe, with only trace amounts of antimatter detected. The mystery of the missing antimatter has puzzled scientists for decades. Several potential explanations have been proposed to account for this asymmetry. One possibility is that there was a slight initial imbalance between matter and antimatter. This imbalance could have resulted in a small excess of matter, leading to the observed dominance. Another explanation is that there are fundamental differences in the properties of matter and antimatter that cause them to behave differently. This could be related to processes that occurred during the early stages of the universe, such as violations of certain symmetries or interactions that favored the creation of matter over antimatter. Experiments conducted at particle accelerators, such as the Large Hadron Collider, aim to study the behavior of matter and antimatter in more detail and potentially shed light on this puzzle. While the Big Bang theory is the prevailing model for the origin and evolution of the universe, there are alternative cosmological models that challenge its assumptions and offer different perspectives. These alternative models propose different mechanisms and explanations for the universe's existence and evolution. Let's explore one example, the steady-state theory, as an alternative to the Big Bang theory. Steady-state theory. The steady-state theory suggests that the universe has always existed and is in a state of continuous expansion. It opposes the idea of a singular beginning or a Big Bang event. According to this theory, matter is continually created throughout the universe to maintain a constant average density, allowing the expansion to persist indefinitely. In the steady-state model, the universe appears the same at any given point in its history, hence the name steady-state. The continuous creation of matter is proposed to occur at a rate that balances the expansion and maintains a constant density. This theory suggests that the universe is infinite in both space and time. The steady-state theory offers an alternative to the Big Bang's singular beginning and the need for inflation to explain the observed uniformity of the universe. It challenges the notion that the universe had a finite starting point and that its current structure and properties are the result of a single cosmic event. It's important to note that the steady-state theory has fallen out of favor among most scientists due to various observational and theoretical challenges it faces. For example, The discovery of the cosmic microwave background radiation, which is highly consistent with the predictions of the Big Bang Theory, provides strong evidence against the steady-state model. However, it is still valuable to consider alternative models and ideas in scientific inquiry, as they can offer unique perspectives and help refine our understanding of the universe. While the Big Bang Theory has gained significant support over the years, it is essential to acknowledge the potential flaws and alternative perspectives. The singularity paradox, the horizon and flatness problems, the absence of antimatter, and the reliance on dark matter and dark energy are just a few areas where doubts emerge. Exploring alternative cosmological models and encouraging ongoing research can lead to a deeper understanding of our universe's origin. Thank you for joining us on this journey of exploration and discovery. Don't forget to subscribe to our channel for more thought-provoking content and stay tuned for future updates as we delve deeper into the fascinating mysteries of the cosmos. Until then, keep questioning, keep exploring, and keep expanding your horizons.